speaker is Eugenia Cheng from Sheffield, and she will talk about the periodic table and categories.
Thank you. First of all, I'd like to thank Bob and Andreas for organising this very interesting series of workshops and for inviting me to speak about this. This talk is going to be introductory, and I should try not to bore anybody. I was amused in Tom's talk. You can infer from that what you will. Right. So here's the plan. The periodic table is about degenerate n categories. So first of all, I'll explain a little bit what degeneracy is. Then I'll talk about the Ekman Hilton argument, which is what we use to work with degenerate n categories and to show that they produce these rather interesting patterns that fit into a table which is called the periodic table. Then I'll talk about some inconvenient things that happen, which mean that the periodic table isn't quite as convenient as we'd like it to be, although it's very, very compelling when you first see it. It's just that when you look at it a bit more closely, it goes a little bit wrong. I'll talk about higher maps between degenerate n categories as well, which actually make the periodic table go even wronger. And then I'll talk about the stabilisation that happens in the periodic table, which is one of the most important reasons for studying the periodic table, because in some of the key examples, what we're really after is the stable case, and I'll explain what that means then. And then finally, I'll briefly talk about other reasons to care. There are lots of reasons to care about the periodic table. Quickly, the periodic table was hypothesized by Baez and Dolan, along with several other famous hypotheses that they proposed in this paper. I did some work on it with Nick Gursky in low dimensions. There's the bi-category one and there's the tri-category one. So if you want to read some more about that, then that's where you can find it. Okay, so what does degeneracy in n categories mean? Well, a k-degenerate n category, a k-fold degenerate n category, is an n category which has only one zero cell in a fit of uncoordinatedness. I'm calling them cells rather than morphisms. So where Tom referred to zero morphisms and one morphisms and so on, I'm going to call them zero cells and one cells. So we've only got one zero cell, and we've only got one one cell, we've only got one two cell, all the way down to k minus 1. So the first non-trivial dimension is going to be k. So you can get awfully confused when you're actually working with these because your indexing can go wrong all over the place. And it gets even worse because the main point about this is that you then do a dimension shift. Because your bottom dimensions are trivial, you want to ignore them and only consider the top dimensions. So how does this work? You used to have an n category, but because the bottom k dimensions are trivial, you're going to regard it as an n minus k category because you just take the n minus k top non-trivial dimensions. So your old zero cells and your old one cells and so on, all the way up to your old k minus 1 cells, are all trivial, so you ignore them. So your old k cells become new zero cells, and your old k plus 1 cells become new 1 cells, and so on all the way down to your n cells, and so that gives you n minus k cells on the other side. Baez and Dolan actually do it the other way around. So they start with an n plus k category, with k trivial dimensions at the bottom, and end up with an n category. So you have to keep your wits about you when you're dealing with these numbers. So let's have a look at some basic examples. Degenerate categories are quite famous. A category with only one object is a monoid. Why is that true? So let's have a look at what happens when we do this dimension shift. In the old category, well, categories have objects and morphisms. The objects in this case are trivial, so we ignore them. The morphisms we now regard as objects in the monoid. And why is it a monoid? Well, categories have composition of morphisms, and this becomes a multiplication of objects. Because there's only one object in our category, every morphism can be composed with every other morphism. And so that's just like a multiplication, really. So when we regard it as a monoid, that does give us a multiplication of our objects. And the identity becomes a unit, and all the axioms in the category become the axioms in the monoid. So it all works out quite nicely. I have a distinct recollection of the first time I saw this fact in approximately lecture 1 of part 3 category theory. And I remember feeling like the ground had been pulled from underneath me. I'm now very used to this fact, but I still remember feeling very much like the ground had been pulled from underneath me. So what about degenerate bi-categories? A bicategory with only one object is a monoidal category. It's very similar, except we've got one extra dimension to deal with. So in the old bicategory, we're going to perform this dimension shift and see what happens to give us a new monoidal category. So the 0 cells, in the bicategory we've got 0 cells, 1 cells and 2 cells. So the 0 cells are trivial, we've only got one trivial dimension. So now the 1 cells are going to become objects in our monoidal category. The 2 cells become morphisms, and now we've got several kinds of composition in a bicategory. We've got composition of 1 cells, and that becomes some kind of tensor product of objects on the other side. We've got horizontal composition of 2 cells, and that gives us a tensor product of morphisms. And then we've got vertical composition of 2 cells, and that becomes ordinary composition of morphisms. If you look at the little double arrow in here, its source is this 1 cell, and its target is this other 1 cell. So if you just stick them end to end, you get something that's just like ordinary composition. Whereas here, you're not sticking them end to end, which is why it's a sort of tensor product of morphisms instead. And that basically, in very rough sketch, gives us a monoidal category. So in general, in a K-degenerate category, we've got the fact that composition of K cells is going to become some kind of tensor product. But we've got K different types of composition. So the composition of K cells, the K cells have become 0 cells in the nucleus. So they're all composable, so they become something like a tensor product. But we've got K different types of tensor product now, because we had, in our original N category, K different types of K cells. Because Tom drew some pictures of some composition of 3 cells. So for 2 cells, you have 2 different kinds of composition. For 3 cells, you have 3 different kinds of composition. For 4 cells, you have 4 different kinds of composition. Spot the pattern. For K cells, you have K different kinds. Because you can stick them together along any dimension of their boundary cell. So that gives us K different directions in which we can do it. So, for example, if we're 2 degenerate, then our bottom dimension is 2 cells. We can compose them horizontally, and that gives us one kind of tensor product. We can compose them vertically, and that gives us another. And I've indexed them according to the dimension of cell along which we're composing. So here, this is the boundary cell along which we're composing. It's a 0 cell, so I've called that tensor sub-0. And here, the dimension of boundary cell is 1 cell. That's the one along which we're composing, so I've called that tensor 1. So you might go, what happens here? We've got 2 kinds of tensor product on our resulting structure. And if we're 3 degenerate, then it's going to be even more ish, because our bottom dimension is now 3 cells. We've got composition along a bounding 0 cell. We've got composition along a bounding 1 cell. That gives us another tensor product. And we've got composition along bounding 2 cells. So that gives us 3 kinds of tensor product. So we go, what's going on here? Well, there is, as you might hope, some rule, some axiom governing the interaction between these different kinds of tensor products. And this comes from the interchange laws inside an N category. So in an N category, we have all these different kinds of composition. There's got to be some way in which they interact. And it's things like this. So it says, if you've got 4 2 cells in this configuration, you have a choice about what order you do the composition in. You can either compose along the 0 cells at the top and the 0 cells at the bottom, and then do the vertical thing. Or you can do the vertical thing on the left and the vertical thing on the right, and then do them horizontally afterwards. And in a bicategory, these are equal. But in any higher dimension of category, they're not necessarily equal, but there's going to be some isomorphism or weak isomorphism equivalence thing mediating in between them, witnessing the fact that they're as much the same as you want them to be, but they're not actually the same. Of course, then you've got to have, this is one of the things that makes weak and N categories so complicated, because these things then have to satisfy some other axioms to make sure that they were coherent enough, and so on and so on and so on. I'm not really going to say much more about that, except that if this is a 2 degenerate N category, then this is going to become some rule about the 2 different kinds of tensor product, right? So this is going to become this, an isomorphism between this way of having the 2 different kinds of tensor product and this way of having the 2 kinds of tensor product. And this is a form of distributivity. And we have analogous coherent cells at every dimension interacting between every different dimension of tensor product as well. And this is, broadly speaking, called K-tuply monoidal. So you start with K different monoidal structures, then you have these things governing the interaction between them, and this is some kind of K-tuply monoidal. So the slogan for the periodic table is that K degenerate n categories sort of are K-tuply monoidal n-1 categories. Now, in the original Baez-Dolan work, they actually just refer to them as, they just sort of define K-tuply monoidal n-k categories to be that. What I'm hoping to show in the process of explaining this stuff is that in fact these things are sort of different, and that there is a process of going from here to here does involve some work. However, the periodic table tells us, is a hypothesis about what kinds of structures you're actually supposed to get out of here. Because it turns out you don't end up with K different monoidal structures. You end up with something a bit more interesting, perhaps, than that. So this part is only part of the point. The real point is what do those K monoidal structures become? Okay, are there any questions about this so far? So the periodic table is a table. It's not actually periodic, which might make you wonder why it's called a periodic table, but of course it brings to mind the periodic table of the elements. And one of the points of the periodic table of the elements is, yes, it's periodic, but also it enables us to make predictions about elements existing before we actually kind of find them. So this table enables us to predict some things about higher dimensional structures before we really got our hands on them properly. So let's start. I'm going to start with sets up here. So these are like 0 categories. And what's going to happen is that along here we're going to increase the dimension of category, and down here we're going to increase the number of trivial dimensions that we have. So here we have an ordinary category, and now I'm going to consider one degenerate categories. So this is my diagonal left arrow says what happens if you consider the one object version of them. So you get monoids, and that's a category with only one object, but really it's a set with a multiplication. That's why it's gone into this column here. This column is all going to be sets with some extra structure, and this column is going to be categories with some extra structure. Okay, so let's try starting with 2 categories and looking at the one object version of those. So that's, we've just seen, is a monoidal category. That's a 2 category with only one object. But now we've gone into the category column, we can do this again. Right, so we can think about bicategories that are doubly degenerate, that is, they've only got one 0 cell and one 1 cell, and that's going to take us over here into this column. We've only got one non-trivial dimension, so it's some kind of set, and it turns out to be a commutative monoid. So you think that it's going to have 2 kinds of multiplication, but it turns out, this is the key use of the Ekman Hilton argument, it turns out that those 2 multiplications have to be the same and commutative. So we get commutative monoids there. And then we can try 3 categories. If we take a one object 3 category, we get a monoidal 2 category, in just the same way that we got monoidal categories out of degenerate 2 categories. So then we can think about one object versions of those. So now we're talking about a 3 category with only one 1 cell. And that turns out to be a braided monoidal category, and I'll explain that a bit more later. But you can think of it as something that's almost commutative, but sort of weakly so. And if you then go down one more column, and you're going to look at 3 categories with only one 2 cell. So we're only going to have one non-trivial dimension at the top, so it's going to come down into this column and become some kind of set with extra structure. And it turns out to be just the same as the one above it. You still only get commutative monoids out. So this is some kind of stabilisation property, which says that you can keep trying to stuff more multiplications into something, but because of the interaction constraints between them, there's a limit to the number of multiplications you can stuff in, and at some point it stabilises, and the more you stuff in, nothing happens, and you just keep getting the same thing back out again. So you can stuff in another one, and you still get commutative monoids, and you stuff in another one, and you keep going. So all the way down this column. At this point, nothing more is going to happen. You just keep getting commutative monoids out. So that's the stabilisation that I'm going to talk about a bit later. Now, if you stuff in another monoidal structure here, you don't get another one. You just sort of make this one a bit better. So this is the rather interesting fact as you come down here. Actually, while we stuck in more monoidal structures, all they ended up doing really was making the previous monoidal structure better behave. So at this point, we can say that that was, I haven't got enough room here, but that was going to be a 4 has 4 category here, and then that becomes monoidal 3 category, and then braided monoidal 2 category, then this symmetric thing, and then here we've already got into the stable part. So now, this is the stable part here. So if we stuff in another monoidal structure there, we still only get symmetric monoidal categories. And this is a 5 category with only 1 free cell. And on we go, notching down here. I've often wanted to have a little mini periodic table, kind of credit card size one that I can laminate and carry around with me at all times, so that whenever I'm talking about symmetric monoidal, I can whip it out and go, oh yes, that's a 7 category with only 1 4 cell. Right. So this one here was a 5 category with only 1 3 cell. What was it when it was here? Well, it's something in between braided monoidal and symmetric monoidal. If you look at this pattern here, we started here with just a multiplication and then it became commutative. In this column, one way you can think about it is that the commutative bit is here, and there's something sort of in between not commutative and commutative. And that's this braiding model thing. So here, there's even more things in between not commutative and completely commutative. And this is something called the selective monoidal 2 category, which came from this diagonal. And after that, we get to the symmetric. So you can see this diagonal here is where all the symmetric things will be. And so here, there's going to be even more stuff in between. So we're going to get selective monoidal 3 categories there, something which is yet to have a name, as far as I know. And then we get to the stable part. So this is the top left-hand corner of the periodic table. You see, I haven't drawn boundaries here because it keeps going all the way down there. It keeps going all the way down here as well. So that is the periodic table. Are there any questions about that?
Can you
Yes.
probably repeat why, because of the degeneracy things become commutative?
Yes. So what I'm going to do next is explain how we get these things. I just thought I'd show you the whole picture first. Are there any other questions? Yes.
How much of these categories have been really constructed from scratch? I mean, how much of them are postulated? I mean, the beginning, of course, is no, but later.
So, Todd Trimble has a definition of tetracategory. That's the weak 4 categories, which he's written out in quite a lot of detail, and it's available on the internet. The diagrams are rather large, so it's not clear quite how to publish it. So the 3 categories were done by Gordon Power and Street and redone in a more algebraic way by Nick Gersky in his thesis. And this part of the periodic table Nick and I have worked out in some gory detail, a little bit of which I'll show you later.
And what about 3 stars? Are there also...
No,
No.
I don't think so. Has anyone done it? Anyone? Anyone? No? Right.
Sure, claims to have done that.
He did a semi-strict version. So
That's right.
Krantz was doing something where he was looking at the coherence question. So he was trying to answer the question: what is the correct semi-strict version of n category to which every n category should be equivalent? And those were called Tesi, and he had some papers about seleptes. No one's really taken that any further, I don't think. And it was quite combinatorial. It's a bit of a brain. Yes. Yeah.
How much of this structure is conjecture and how much is known?
And the table.
Yeah.
Well, I'll tell you more about that as we go along. So it's known at some level, but making it completely precise, making this table completely precise turns out to be very difficult. Okay, so let me just first give you the idea of how you use the Ekman Hilton argument to get commutativity out of nowhere, really. So the Ekman Hilton argument is arguably nothing to do with Ekman or Hilton, but it was first used to show that the higher homotopy groups are orthopedic. It's a rather nice argument if you draw pictures in homotopy, and it's also a rather nice argument if you draw bicategory pictures. So anyway, what's the argument? You can just say it like this. If A is a set with 2 binary operations, such that they're both unital with the same unit, that's very important, and that they satisfy this distributivity, which you might recognize from earlier, which says that, then, in fact, those 2 operations are the same operation, and this operation is commutative. So, I recently looked this up on Wikipedia, and it was rather odd. There was something on the Wikipedia page called the Ekman Hilton argument that just wasn't the Ekman Hilton argument. And it wasn't even trying to be the Ekman Hilton argument. It was maths, but it wasn't anything to do with Ekman. So I wrote very quickly what the Ekman, I basically wrote that, and I proved it very fast. So you can just write down some algebra to prove it, and it doesn't look at all explanatory of anything. Whereas if you draw some pictures, it turns out to be quite nice looking, and then you can extract the algebra back out of it again. So the reason that this is useful for a bicategory, so we have these interchange laws in a bicategory. And in a bicategory, that becomes this, as I said, and this is exactly that condition that we need to apply the Ekman Hilton argument, where star, in this case, is the tensor product along the composition along 0 cells, and this circle is composition along 1 cells. So I like to draw this on a clock face. I call this the Ekman Hilton clock, because it turns out there are 12 stages that you do. And you start at 12 o'clock, so here's alpha and beta, and they're composed along their bounding 0 cell. So what we want to do is we want to be able to move them around each other to show that we can get them the other way around and it's the same thing. So the first step is, I've done alpha in red and beta in blue because it's quite small and I hope that will make it more visible. So the first step is that you insert some identities here vertically, and then you apply the interchange rule. Then you get rid of these identities horizontally, so now we've got alpha and beta vertically composed. So far we've shown that the horizontal composition and this vertical one are in fact the same. So furthermore, we can keep going around this clock, and when we get to 6 o'clock, we'll have shown that it's commutative, because now we can insert some horizontal units again, we can apply the interchange law, and then we can get them side by side the other way around. And of course, sort of dually, we can go around again and get all the way back up to 12 o'clock. And if you really feel like it, you can write down these things in algebra. Goodness knows why anyone would feel like it, but here we are. So this is what it looks like if you write it down. There's the interchange law, on we go. So clock. I did actually make this into a clock, but I did it in Chicago. It was a bit fragile, so I wasn't able to bring it back across the Atlantic with me. Are there any questions about that? It wasn't a very good clock anyway, kept getting stuck. Right, so you might ask what happens if we go up a dimension. So in a bicategory, these are all equalities. In a tricategory, they aren't. They're sort of they're isomorphisms of some kind in a coherent way. And so we use a categorified Ekman Hilton argument. So everywhere, when you categorify things, the idea is that sets turn into categories and equalities between things turn into isomorphisms between things. It's much more complicated than that. You might hope from that brief explanation that there's some kind of black box into which you can stick anything and out will pop a categorified version of it. If that were true, then, well, it'd be great. But it's much more complicated than that. So I'm going to go over this rather quickly because it's not exactly true. So you sort of want to say that if you have isomorphisms, coherent isomorphisms like this, then you get coherent isomorphisms where between the two different kinds of tensor products and showing that they're sort of commutative up to isomorphism. You might recognise this kind of thing. If you have a whole load of these things in a coherent way, that's called abrading. So abrading on a tensor product is some coherent isomorphisms between A tensor B and B tensor A. And, well, there's a slight problem with this argument, which is that horizontal composition of two cells isn't actually strictly unital. So this was already a problem in a bicategory, actually, that horizontal composition wasn't strictly unital. We kind of needed it to be to apply the Ekman Hilton argument. That is to say that this isn't actually alpha. The reason it's not is because along here we have an identity 1 cell, and along here we have an identity 1 cell. So when we compose them, actually at the top we'll get the identity composed with the identity. And in a bicategory that's not necessarily the identity, because everything is weak. We can get around this problem by using the following more complicated looking operation, like this, by applying some unit constraints above and below. And then you sort of do the whole thing using that instead. And it turns out to be okay, but this gets worse and worse as we increase dimensions. So when you're thinking about n categories, it's important to remember that everything gets worse as you increase dimensions. So many things are true in bicategories. Bicategories can give you a very bad impression, well, an overly good impression of what's going on, because many more things are true than really ought to be true. So you can always assume that it gets worse as you increase dimensions. So to do doubly degenerate tri-categories, so here we've got 2 dimensions degenerate at the bottom. 2 cells are going to become objects. 3 cells become morphisms. Composition of 2 cells, well, that becomes 1 composition becomes a tensor product, but 0 composition isn't quite a tensor product anymore. It's close, but it's not quite. And so it takes a rather lengthy calculation to show that this all works out. So in Gordon, Power and Street, the thing about tri-categories, they just kind of say that a doubly degenerate tri-category is clearly a braided monoid category. It takes quite a lot of work actually to go through the details and construct what that braided monoid category is and show that it is one. And Nick and I did this when we were staying at the Fields Institute, and I thought I'd show you some of the diagrams that we drew on the boards there to show that this is true. Here's another one. So it involves showing some 2-dimensional commutative diagram. So this, that, which shows clearly that it's braided. So in general, the composition along bounding k minus 1 cells does become a tensor product, but the composition along the bounding I cells gets further and further from actually being a tensor product as I gets smaller towards 0. So the moral of that is that we thought that k degenerate n categories were k2 monoidal n minus k categories, but actually it takes some effort to get there, and that's not quite, it's not quite true. Right. Are there any questions about that? Yes.
So when you say it's not quite true, do you mean that they are different classes, or do you just mean it's quite hard to show?
Well, it's not a tensor product, so you have to use something. So when I showed you the diagram of what you do in bicategory instead, where you put some unit constraints above and below, that becomes, if you do that, then you get something that really is a tensor product. So you have to do that instead. And then the higher, the more dimensions you have, the more of those things that stick on. Are there any other questions? Right. So that's the first problem. Then the next problem is that we get some inconvenient elements. This was, I think, well, it was certainly first pointed out to me by Tom Leinster, that a bicategory with only 1 0 cell X, we can call it anything we want because there's only one of them, and 1 1 cell, which has to be the identity on X, is, well, it's not precisely a commutative monoid. It's precisely a commutative monoid with a distinguished invertible element. Now that distinguished invertible element may or may not be the identity. It doesn't have to be the identity. So we get some extra kind of pointing on our commutative monoid. Why is that true? Well, it comes from the coherence constraints in a bicategory. So we haven't talked about this very much, but in a bicategory, you're only associative up to isomorphism, but it's a specified isomorphism that you need to be able to carry around with you to check that everything's working okay. And there are also left and right unit constraints that you have to specify to check that everything's working properly. So if we look again at this situation where we've got an old bicategory and a new commutative monoid, the 0 and 1 cells are trivial. 2 cells have become elements of the monoid. And coherence isomorphisms over here are 2 cells. So they're going to become invertible elements of the monoid over there. So what are the coherence isomorphisms that we've got? We might expect 3 of them because we've got the associativity constraints and the left and right unit constraints. But in fact, we can use the axioms for a bicategory. So there's an associativity pentagon, which if you've only got 1 0 cell and 1 1 cell around, it completely reduces down to saying that a squared equals a cubed, which means that a has to be 1, because a is invertible. And then, in any bicategory, the left unit constraint on I is the same as the right unit constraint on I being a unit. So that's proved by Joel and Streep. So our left and right unit constraints end up being the same. So one of them was the identity, and 2 of them have become the same. So actually we've got 1 of them. So we've just got 1 invertible M. And there's just nothing you can do with it. It's just there. So you might think to yourself, okay, well, can we fix this using higher morphisms? So one of the morals that Tom mentioned of all this is that we shouldn't just think about n categories by themselves, we should think about the totalities of them. And this is sort of one of the morals of category theory, not to just look at structures in isolation, but to look at the totalities that they form and the morphisms between them. So we think, okay, these aren't exactly the same as commutative monoids. Maybe the totalities of them will actually turn out to be the same, and that will save us at the last minute. So let's try that. Tom Leinster also pointed out that if you look at doubly degenerate bicategories and weak functors between them, then you don't get precisely a monoid homomorphism. You get a monoid homomorphism together with the distinguished invertible element. Oh no, where does this come from? Well, a homomorphism is only weakly functorial, but it's weakly functorial up to some coherence isomorphisms. So this is the one, if this was actually functorial, these two would be equal, right? But now we've got some coherence isomorphism mediating in between them. And again, for the unit, we have another coherence isomorphism mediating too. So you might think there were going to be two distinguished invertible elements, but if you stare at the axioms for a while, you discover that one of them can be expressed in terms of the other. So there's actually one. So what have we got so far? We've got commutative monoids with a distinguished invertible element, and then we've got homomorphisms between them with a distinguished invertible element. So you can go, let's try going one further. A weak transformation between two such things is the assertion that the two morphisms are the same. So actually this has rescued us. There was no reference to the distinguished invertible element here, so if we look at these totalities, that's fine. So this has rescued us. Unfortunately, if we take this to its logical conclusion and look at the modifications between bicategories, this messes us up again, because a modification between them is just a distinguished element in the right-hand side. So you might think to ourselves, okay, we should have just stopped while we were ahead. We should have stopped and just forgot about the modifications for a while. So if we compare the totalities of doubly degenerate bicategories with the totality of commutative monoids, on the left-hand side, we've got doubly degenerate bicategories, we've got weak functors between them, we've got weak transformations between those, and we've got modifications between those. And we can look at them at various different levels. On the right-hand side, we've got commutative monoids, homomorphisms between them. Nothing else happens, so for the 3 cells, we better throw in some identities. For the 2 cells, and for the 3 cells, we'll throw in some more identities. And we can now try comparing these at the level of categories. And it turns out that this is not an equivalence of categories because of all those distinguished invertible elements floating around. If we compare them at the level of bicategories, we do get an equivalence of bicategories. But if we go all the way and compare them at the level of tricategories, we get messed up again. So the moral of that story is that you have to be rather careful about what kind of totality you decide to use. If we do this for triply degenerate tricategories, this is here, so we're supposed to be still commutative monoids. It's even worse. As I said, you can expect everything to get worse as you increase dimensions. So we're still going to compare them with the totality of commutative monoids. So we have triply degenerate tricategories, functors between them, things called tri-modifications and tri-transformations and tri-modifications, and then at the top level we have things called perturbations between them. On the right, we're going to use commutative monoids, homomorphisms, and a bunch of identities between them. Incidentally, this is actually a commutative monoid with, I forget how many invertible elements, I think 5. And this is a weak functor with, I think, 8. I think that's what it is. I can't quite remember. Anyway, so we can try comparing at the level of categories, but this does not form a category. So we can't do it. We can try comparing at the level of bicategories, but this does not form a bicategory. So we can't do that either. We can try comparing at the level of tricategories, and we do get an equivalence, but again, the top level messes us up, so we can try comparing at the level of tetracategories, and it's not an equivalence again. So again, we have to be rather careful about where we're doing our comparison. That, in general, is an issue whenever we have more than 2 degenerate dimensions at the bottom. So this issue goes away for non-algebraic definitions. So there are 2 kinds of definition. There's algebraic definitions and non-algebraic. The algebraic ones are where you specify everything in sight. And the non-algebraic ones are where you don't specify them, you just say that something has to exist. So you say there has to exist an isomorphism here, there has to exist. Sometimes you even only say there has to exist a composition, you don't actually say what it is. So if you go around doing that, you don't have any specified isomorphism, so you don't get any distinguished invertible elements. So it's possible that that all goes away. But there aren't any non-algebraic definitions around that are very good for doing degeneracy too at the moment. I don't want to go into that too much. But in any case, there are other problems. Before I talk about those other problems, are there any questions? Yes.
Why are you so desperate to get rid of these chosen, these canonical invertible elements?
Because they mean that we can't compare the totalities with the things in the periodic table properly.
We could do a new periodic table that says
That
this is a
involves-
thing with a chosen element, and this is some other thing with two chosen elements.
We could do that. It's true. It would sort of mess up stability a bit, because as we go down that column, we get more and more chosen elements. So we'd have to change slightly what stability says. It's not clear to us. Well, it's not clear to some of us at the moment how to deal with this. I'll talk about various ways of dealing with it a bit later. Are there any other questions? Yeah.
So, I didn't understand how it's possible if you have categories which are not equivalent, right? And then you, upgrade them to two categories, they become equivalent.
Because you have a distinguished invertible element, but if your morphism between them isn't required to preserve the distinguished invertible element, then it just goes away. So if you think about pointed sets and morphisms between them, then the morphisms are required to preserve the pointing, and so that means you're different from just the category sets. However, if you weren't required to preserve the pointing, then you would be equivalent to just sets. Are there any other questions? Right, okay. So let's talk about some other problems involving higher morphisms. So when you look at degenerate bicategories, you're supposed to get monoidal categories out. A weak functor between them is indeed a monoidal functor, that's perfectly fine. However, transformations between them are really quite different from monoidal transformations. This is not an issue of distinguished invertible elements, it's just an issue. So why is this true? A transformation, we haven't really talked very much about these things, but if you know what a natural transformation between functors is, a transformation is sort of similar. I'll just tell you what you get. So what you get between degenerate bicategories is an object together with, so it sort of is to do with degenerate elements actually, because you get distinguished elements, because you just get an object together with components that go like this. So this is probably an isomorphism if you're doing weak transformations. It satisfies some axioms. This is very different from what a monoidal transformation between monoidal functors ought to be. So a monoidal transformation has components that just go from f of a to g of a like ordinary natural transformations do. So if you compare this with this, there are several problems. One is that there's an alpha getting in everybody's way. Another is that this is fundamentally going in the wrong direction. And the other is that this is sort of supposed to be an isomorphism, and this isn't necessarily supposed to be an isomorphism. So you might think that we can fix this by, well, we can try looking at modifications, that doesn't help at all. We can try restricting to the case where that distinguished element was the unit. And fixing the invertibility, or that should say op-lax. So we fix the direction by going op, and we fix the non-invertibility by doing lax transformations. This doesn't help because, well, lots of reasons. One is that it's not closed under composition. Another is that lax transformations behave truly awfully. So maybe you can construct the closure under composition. That doesn't work either. This is for increasingly technical reasons, so I'm not going to tell you what they are. But you keep trying, and it just keeps resisting. So one thing you can do is consider icons, which is something that Steve Lack has proposed recently. I won't say what they are because this is sort of a comment for the experts, but if you do consider icons, then everything works, but you've really changed your structure. So this is no longer a sub-tricategory of bicat, you've really changed something. So it gives you the right thing, and it's quite useful because Nick and I use this to define the totality of monoidal bicategories very precisely. And so probably if you did higher dimensional icons and you kept going, then you could do monoidal everything else is very precisely. But it's a kind of different approach. So the moral of this is that we should probably have proceeded in two separate stages in the periodic table. So going from K degenerate n categories to K tuply monoidal n categories is one thing that's all by itself sort of a problem. Going from K tuply monoidal n categories to the periodic table probably works much better. And so I think that this part is a part that probably works quite well. You keep using higher dimensional Ekman Hilton arguments. Michael Botanin has done some work in generalizing the Ekman Hilton arguments, and recently Nick Gursky has done some more work on that as well. So the moral so far is that the second step of this is much more precise than the first step, and so I think it's helpful to separate them out. Are there any questions about that? Okay. So, try not to take too long, but I'd like to say some things about what this is all for now. What's this all for? So one of the things we're interested in is this stabilisation result. I've put it in red now, the bits that this is the stable thing, showing that if you go beyond this, nothing else happens. And these stable things are, well, the idea is that there's a limit to how many monoidal structures you can fit into an n category. And the limit is n plus 2. And if you know your stable homotopy theory, you might observe that that's the same place where homotopies get stable as well. This is not a coincidence, but I'm not going to go into that very much. So the idea is that adding a monoidal structure has the effect actually of making existing monoidal structure more symmetric, and eventually you become maximally symmetric, so you get symmetric monoidal n categories out. And this is where so you go down here, you become more and more symmetric. So in a way, it's a way of achieving symmetric monoidal n categories. And you might ask yourself, why we want to proceed down here step by step? Why don't we just go straight in there and give ourselves symmetric monoidal n categories? Well, it gives us quite a nice way of thinking about the TQFT hypothesis and tangles and cobordisms with corners that Tom was talking about. So this hypothesis says that the n category of which n-dimensional extended TQFTs are representations, so is the free, stable, weak n category with duals on one object. And the idea is that you get there bit by bit. You consider manifolds embedded in some dimension, and that gives you some entry in the periodic table that isn't quite stable. And then you increase your dimensions of your manifolds embedded in things until they become more or less like abstract manifolds, which is what you actually want. And then, but by the periodic table, by the stabilisation thing, you discover that you can just proceed as far as the stabilisation point. And that n plus 2 is exactly the same place where, if you look at manifolds embedded in some dimension, you become just like abstract manifolds as well. So this is the motivation between this hypothesis and why you might want to proceed bit by bit down the periodic table rather than just going right in at the symmetric place. Okay, are there any questions about that? So finally, some other reasons to care about this. If we start with an n category and restrict to a single zero cell, we get a degenerate n category. So sometimes we're interested in just restricting our attention, seeing what happens on a single point. And this is very much like in topology, when you start by looking at paths in a space and then you just pick a base point and look at loops on that point. You get a loop space. And if you look at a doubly degenerate n category, that's like a double loop space. And there are many more connections with loop spaces and topology and the Freudenthal suspension theorem and things like that. So I'm not going to talk much about this because I don't think this is entirely a topological audience. But also, you can think that degenerate n categories somehow capture the essence of weak n categories. Coherence, Tom already said this, coherence tells us that every weak 2 category is 2 equivalent to a strict 2 category. But not every weak 3 category is 3 equivalent to a strict 3 category. And basically, the whole reason for this is braidings. So the thing that you can sort of think that the existence of braided monoidal categories as opposed to symmetric ones is exactly the same fact as the existence of weak 3 categories that really aren't strict. And it's sort of the same fact as well as the fact that strict 3 groupoids do not model homotopy 3 types and that you need some kind of weak ones instead. And the whole obstruction is in the fact that you have braidings. And braidings come about because you've got non-trivial morphisms between identity cells. So the Ekman Hilton argument works because everything's going between an identity. So because it's sort of, you've got too much room to move. If you're a morphism between identities, you can kind of move all over the place, and that makes things more complicated. This sort of is the whole obstruction to becoming strict. And so all the difficulties come from having non-trivial morphisms between identity cells. So I'd like to end on this slogan, which is that the periodic table somehow measures the difference between weak n categories and strict n categories. And as you increase your dimensions, the distance between the top of the periodic table and the bottom gets wider and wider. So that's sort of saying that the distance between weak n categories and strict n categories is getting bigger and bigger and is encapsulated by those entries in the periodic table. So I'll stop there.
Is there some kind of, do people study degenerate infinity categories? And is there some kind of limit down that diagonal of a kind of symmetric monoidal infinity category?
Yeah, that's the idea, that there should be.
And do they appear in nature?
Yeah, so if you do cobordisms, what am I trying to say? You're going to get there with cobordisms eventually? Yes, so if you do cobordisms and you don't stop at the top, so when you do, gosh, this is moving. When you do the n-dimensional version of cobordism, at some point you don't consider any cobordisms beyond a certain dimension, and you mod out by diffeomorphism or something. But if you just keep going with all of them, then you'll get symmetric monoidal omega infinity category of cobordisms. Any other question?
So-
Yeah.
In fact, are there any infinity categories, monoidal infinity categories, that are known not to be symmetric? I mean, either you're going to be completely not symmetric at all, you're right at the top, or you're going to be right at the bottom, you're going to be a symmetric monoidal infinity category. I can't imagine that any sort of occur in nature.
Can you repeat the question?
The question is, are there any naturally occurring infinity categories which are anywhere in between not being monoidal at all and being symmetrically monoidal? Perhaps we should talk about this. I don't share your confidence on that.
I have no confidence on anything.
okay.
That's just
I don't know. Interesting question.
Okay, maybe we can discuss a little further over lunch. So let's thank you again.